So this was the case. Now let's assume that there are two number of stages. I am not drawing the second stage. So what I want to do is I want to design a common mode feedback circuitry. Before going to this, let's ask you one question, very simple question. So if I want to make temperature, I want to measure a temperature. How can I measure temperature? Which will show me equivalent temperature on 7 segment LED, let's say like this. What do you think? I want to measure a temperature which will show me the temperature on this 7 segment LED. What do you think, Gaurav? Or pressure or whatever the quantities are there. If I want to measure them, I want to show it on electronic some setup. So how to measure that? VDC? ADC. So ADC is analog to digital converter. Analog is, but it only understands voltages, right? So this is analog quantity, this is digital. So this indicates there are some number of n number of digital lines. So how to make that temperature, pressure or anything into voltage? So transducers, but how to, which transducer? Okay, so somebody told thermistor. Okay, so what? I have thermistor. So if I connect thermistor directly, it will give voltage. But how? Where to connect? How to connect? So you are saying that thermistor is here, right? So temperature is coming from somewhere in environment. And like thermistor looks like this one, by the way. It looks like resistor. Now, what to do? So, which terminal Opamp and? Okay, so I believe all the answers are wrong, but not going in some constructive way. So how to convert this, let's say, temperature to voltage? There is only one way till now. There is only one way. So if you are studying this course, measurement and what is that? Measurement and measuring instruments, right? Something like this. Electronic measurement, EMMI, or something like that, right? So what this course teach you is all the different transducers for different quantities: temperature, pressure, flow, and level. 4 quantities, 4 different like various transducers, but how to connect them is also part of it. So what it explains, the minimum or the fundamental circuit looks like this one. I am writing R transducer, that one you have to connect it here, like this plus and minus terminal should go here. This circuit is known as what? Wheatstone disk, right? So what will happen? If I am connecting here this some transducer, what will happen at the output?
Sir, any disturbance in R resistor will disturb the...
Yeah, so at balance condition, we want R1 by R2 is equal to R1 by R transducer, right? So if R transducer is exactly equal to R2 at ambient temperature of 27 degree, then everything is fine. Then there is no fluctuation across these two terminal. Or if you are keeping the galvanometer, you must have done it in your school that you are keeping galvanometer and checking whether it's 0 or something else, right? This is the only trick. So if it is 27 degree, I know that output is 0. So I'll say that 0 is nothing but 27. So I have to draw here 27. right, and 0. That you can do it, right, for different voltages. What is a BCD converter you are using in your digital course? You must have done it, right? So this is easy thing. The only difficult thing is this one. But the problem here is the common mode. Still, because this is the pseudo differential circuit, which is suffering from one thing, which is the common mode. So common mode voltage is going to give you some problem. So what people have thought, let's redraw this. And keep something like this. It's a differential amplifier, simple, right? This will give you better common mode rejection because it's not pseudo differential, it's differential. This was one way, and in increment people are using afterwards something called instrumentation amplifier, which needs 3 op-amp configuration. All those things we are doing for only one reason: we want to control the common mode. Instrumentation amplifier require 3 op-amps. So it's a configuration. You can read that in any book. It's given, those who have not studied. But this is very important. Most of the competitive exam they ask, right, for instrumentation amplifier, that's CMRR, all these things. So the thing is, the easiest way to measure some common mode voltage is the ratioed resistances, which is actually taking care of current. So same thing I am going to do it here. Okay. So here, this common mode, output common mode voltage is not the one which I wanted. And if you look at here, this M1 is contributing some resistance. Let's call 1 by GM of 1, which is contributed by this transistor. So the current flowing through this one times 1 by GM1 is going to give me the voltage across this one, or VDS, right? Or if it is not in saturation, it's RO1 or capital RO1. All have different meaning, right? This is channel length modulation resistance, this is on resistance when it's in triode, and this is in saturation, right? So any one of them is going to contribute, multiply by current which is flowing from here, is going to control the output common mode voltage. It's not controlled by input side because it's not pseudo differential, it's a differential. Now what I'm doing, I'm just picking this voltage and I'm picking another voltage this side, and I'm saying that I'm going to sense that common mode voltage or the DC voltage. And as you are saying, we have to keep one comparator, right? At the beginning you are saying that we need to make some comparator, and comparison has to be done by the V reference coming from outside. It's off chip sometimes, and sometimes you are generating on chip. This is going to either increase this I or decrease this I. That is a system level explanation. How to implement, that's the next slide. But the main thing is you have to sense the common mode voltage available in these two. How to sense it? Similar approach what we are doing in actually Wheatstone bridge. Let's use 2 resistances. And the average of these two, if R1 and R2 are equal, then average of these two is available here. You agree with this one? Right? Some voltage is available here, V out CM1 plus V out CM minus. And average of these two is actually here. So if I am like this is, let's say 1.8 volt and this is 0, and if this is 0.75 and this is also 0.75, because at common mode both the voltages will be equal in ideal condition, right? Because everything is same. So common mode will have same potential, so it will average out and it will give me 0.75. But I want how much? The V reference, I need 0.9. which will tune the required current. But this was just sensing the voltage. Now after sensing the voltage, what you can do, okay, so this one, okay, this is another way to sense it, where you are keeping two MOSFETs which are realizing resistances. These two resistances are preferably to keep it in triode or linear mode, because it is much more better value or the linear relation with respect to the potential Vp. So that's why this is used, right? So this is another way to implement same thing. The only thing is how to take further. As I told you, you can, this is folded cascode. It has two stages. I am trying to tune the first stage, so I have picked up the V out CM, or it's V out 1 plus V out 2 divided by 2, and it will compare with the V reference. Generally you want to give, let's say, 0.9 volt for VDD of 1.8. If it is not, then what is going to happen? It will make these particular current sources in on mode, because output of this one will be either 1.8 or 0. Do you agree with this one? Because it's in open loop, it's not in feedback. So this is a comparator. This is not actually op-amp in feedback, so output is not some smaller value. It will be either VDD or 0, either VDD or ground, because it compares. If this is 1.0 volt, what will be the output? 1.8, because plus is higher than minus, so VDD will be available. If this one is 0.8, it's visible, right? If it is 0.8, then output is 0, right? So that's how you can make particular current sources on or off. So it's not the complete picture, but in reality what they do, so they are keeping extra transistors in parallel. Can you see this M3 and this M4 are the extra transistors, and if they are on, it will ask for the current. If they are not on, they are off. So it's something like, earlier this for VB1 was already available, so there is a switch through which it's asking for current, or it will have the more current flowing through this one. So indirectly they are increasing the current flowing through this branch, right? More transistors also, not only one, you can have multiple of transistors, and the current flowing through is, if it is I, if this is 2I, if this is 4I, then this is called DAC based tuning. Are you following this, or something is missing, Gaurav?
So what is that?
Okay, yeah. Before that you understood. Before DAC, you understood. DAC is digital to analog converter. So digital to analog converter. Sorry, I missed the word. So it says that how many current sources will be on and off. You can look at these currents are binary weighted. I, 2I, 4I, 8I, and so on. So you can keep many currents in parallel, and whichever current you want to make it on and off, you can do it from one op-amp or maybe many op-amps. So that is called digital to analog converter based tuning. Somebody can sense this and compare, and they can tune the first current also. Rather than tuning this current, they can tune this current also, because there are possibilities that this current is controlled by this transistor, this current is controlled by this, or maybe these two transistors. So third choice, maybe you can control these two transistors by This is also possible. Either of the way you can go. It's not a problem. You can either tune this one, you can tune this one, you can tune this one, so that the current flowing through these two transistors are well controlled and the common mode voltage at the output is within your limit. So these three ways are possible. Okay, so I think other things are not so much important, but before that I can just sign off with one important thing. So till now whatever we have learned was just open loop, or whatever you designed was just open loop, but that's not the true case of your op-amp. Your op-amp has to be in feedback, because with your op-amp you can do three things. You can keep your op-amp in open loop, you can keep that in negative feedback, or you can keep it in positive feedback. If you are keeping open loop, it's not known as op-amp, it's known as comparator, whose output is either VDD or VSS, right? So it's just a comparator. If plus is higher than minus, so plus value is higher than minus value, so if this is 0.9 and this is 0.8, output is VDD. The only thing which we have to understand, this amplifier gain is good enough to take care of this offset voltage, or IOV, input offset voltage. Input offset voltage is nothing but V reference divided by gain, right? So if gain is, let's say 60 dB, there is no problem. It can take care till 1 millivolt, because 60 dB is 1000 volt per volt. So, and if this is 1 volt, right, then Vref by 1 millivolt will give you this one. So comparator is open loop. There is no connection from between output and input side. Now next thing might be, it might be in negative feedback. I can connect this here. Then we learn one more thing. If it is in negative, if I am applying square wave, the output is square wave, but the only thing is the output will have some oscillations. This is happening because of one reason. This op-amp is not first order, it is second order. But if you have designed it with 60-degree phase margin, then the output will not look like this one, but it will look like. So just to see whether your ringing and all these things are happening as per your expectation or not, you have to keep your op-amp in negative feedback, which can measure following things. You can measure slew rate, right? You can measure rise time, you can fall time, delay, jitter, right? All these things you can measure it, which you have not measured in your case. But if you want to measure these things, because this might be the specification, so you have to keep your designed op-amp in negative feedback. You have to connect output voltage with the negative terminal of the input, and you have to apply square wave at the input side. This is what you need to do, right? Just to find out these things. Now there might be one more case where I'm connecting this way. Then what is the output, by the way? It will be always, so this kind of circuit is known as Smith trigger, and this says that Smith trigger is going to oscillate always. It's an oscillator. Using positive feedback you can make always oscillator. So output will be square wave. It will oscillate between plus and VDD and ground, and where it's going to be oscillate you can find out through the triggering point. The triggering point can be decided actually by Smith trigger circuit. You must have studied somewhere, right? So generally if this is the case, right? I'm not going into detail how to design this R1 and R2, so that your duty cycle and all these things will be actually varied, and it will take care of this oscillations frequency, and all these things will be designed through R1 and R2, right? So we are not interested in this one. We are more interested only in negative feedback, right? So I can ask you one more question. I'm drawing very simple circuit. So my agenda is to find out gain of the circuit, but I know that I want to use this circuit in negative feedback only. I'm not interested in positive feedback, right? Because I want to design an op-amp, not Smith trigger, not comparator. So now, okay, after this, let's have this circuit also. Now the question is, when you are doing all these things and you are interested in negative feedback like this, so this is the worst case condition, because output will show the maximum fluctuation in negative feedback with the gain of feedback gain of 1, right? And if you are interested in that, now if it is open loop like this, which you have done it, right, and you have measured V out by V in, right, you have done this one, but this V out by V in may not be the same as this one, because what we are doing here, if there is a sine wave, it's a two-stage. Just look at this. In reality, I want this one. In reality, I want this one. If I don't control it, output will be VDD by 2. If I don't control it, this dotted line will be VDD by 2 if I don't control it. And I want to have it VCMI, exactly same, because you must have studied that if it is an op-amp, whatever you are applying here at the plus terminal, that will go to minus, right? How to make sure that this will happen? It will happen only when whatever the sine wave is here, or DC quantity plus AC quantity, exactly it goes there. Let's forget about right now AC quantity, because AC quantity will take care by this equation when it's in feedback, negative feedback. And if I want to make sure that the DC is same, here I have applied some VCMI plus something, VCM, one side VCMI plus V, another side is actually going to be in negative. When you are going to make this one, you will have different characteristic, because this VCMO is going here, and this VCMO will have a different VCMO2, right? So this VCMO2 is higher than VCMO1, and VCMO1 is higher than VCMI. So maybe you don't have enough headroom. So what I am suggesting, rather than doing this, just to have the same DC condition, just to have the same DC condition of here, which is here, VCMI and VCMI both are equal. What I can do, so unfortunately this is not given in any book, but all the industry people, they are doing this. So let's assume that this is a fully differential. Having same thing is another side, it's also available. So to get the same DC potential, there is a trick that let's add one inductor. which is of bigger size. And what this inductor does, so this is just for simulation, it's not part of inductor, just to make sure that your simulation works the way you want it. Forcefully you want VCMI, these two VCMI equal. So when I'm connecting inductor from here to here, at low frequency, this is short. Depending on what value you are taking, we generally take very high value, right? Let's say 1 Henry. It's in simulation, just in simulation. Not in reality, we are going to connect it. Just to check that whether it's working with the worst case also, you have to do this one. So when you are doing this, whatever the DC potential was available here, it will go here. And when you are going at high frequency, this is open circuit and it will give the gain. At low frequency, this is exactly VCMI or DC potential, whatever you wanted, it's there. So this is what you generally have to do for simulating the op-amp gain, phase, right? So what we have done was little bit incomplete, but without understanding this approach of common mode, we cannot go further. Unfortunately, this is not given in any book.
Sir, do we use inductors for real circuits? Do we use inductors?
No. In some cases we are using, if it is oscillator, yes, we are using, because we need the tank circuit which will resonate, otherwise it will not resonate. Inductor will take lots of area, right? Maybe it will take 1 Henry is a very big number. So if it is 1 millihenry, maybe very easily it will take 10 by 10 micrometer square or higher than that. Depending on the technology, I am talking about 130 nanometer. Right. So that's all for this course, maybe, right?